We've all been there, right?
Yeah.
I want you to picture this very specific moment. You are hunched over your desk, staring at a problem. It could be a spreadsheet, a tricky piece of code, maybe just that inbox that never ever seems to empty. And you've been grinding away at it for what feels like an eternity. Your muscles are tight, your shoulders are, creeping up toward your ears. Then finally you hit send, or the bug fixes, or you find that one missing number, your shoulders drop, your whole body just kind of slumps back in the chair. And you let out this massive, audible, ragged sound. A full, complex exhale that seems to carry the entire weight of the last 4 hours with it.
It is the sound of release, isn't it? It's like the universal sound of the soul hitting the reset button. It's the sigh. And usually when we think of a sigh, we tie it to one of those deep, massive, complicated emotional states, despair, longing, immense frustration, or pure, unadulterated relief, just like you described.
Absolutely. It's that moment that's, immortalized in pop culture, like that famous line from Casablanca that claims, a sigh is just a sigh. But the irony is we know instinctively as human beings that a sigh is never just a sigh. It's a nonverbal broadcast of a massive internal state. It's an instantaneous signal that communicates everything you can't or won't say out loud.
And our sources totally back that up. I mean, if you polled people on the street, they would tell you they associate sighing mainly with those low-intensity negative emotional states, sadness, resignation, or frustration. Especially, and research shows this, when they're trying to solve a puzzle and just can't get there, that deep exhalation is often perceived as giving up, or surrendering to the difficulty of the moment.
Oh, yeah. I've definitely had the I give up sigh after trying to assemble some IKEA furniture with those incomprehensible instructions. But then there's that other sigh. The sigh of absolute relief, maybe after you hit a major deadline or when you finally find your car keys that you were sure were lost forever, is a massive tension release.
Exactly. It's used as a social cue for all this complex emotion, but here is the genuine mind bender. This is the piece of data that flips the entire script on what we think the sigh is. You, the person listening right now, are executing this exact same physiological reflex whether you are heartbroken, solving a puzzle, totally elated, or even if you are sound asleep and perfectly happy. An average healthy adult spontaneously sighs about 12 times every single hour.
Wait, stop. 12 times an hour? That's roughly once every 5 minutes.
Okay.
So you're telling me I've probably sighed at least 4 times since we started this deep dive, and I didn't even notice. No way.
You did, and no, you didn't notice. Because it is not emotion driving those frequent spontaneous sighs. It is a life-sustaining, fundamental physiological reflex. It is a critical piece of survival machinery hidden in plain sight.
So our mission today is to show you why that seemingly mundane, automatic deep breath is so much more than a feeling. Our sources reveal that the sigh is actually a critical piece of survival machinery, governed by a tiny, ultra-specific circuit in your ancient brainstem. And paradoxically, because of how that circuit is wired, the voluntary sigh is also the single most effective tool you can use to immediately re-engineer your mood and anxiety in real time. We've got the sources detailing the mechanics, the neurology, and the psychology. Okay, let's unpack this and dive deep into the secret life of the sigh. To really understand the sheer necessity of the sigh, we have to start with the physiological villain in this story. This is the problem it evolved to solve, the constant threat of lung collapse.
It's absolutely the starting point. When we breathe normally, what scientists call eumaic breathing, we're taking relatively shallow, repetitive breaths, just, in and out. Inside your lungs, you have this incredible network of delicate air sacs called alveoli. There are hundreds of millions of them, and this is where the vital exchange happens. Oxygen in, carbon dioxide out.
So that's the engine room of the whole body.
Precisely. But here's the problem. If you keep taking those repetitive, shallow breaths, the mechanics of those delicate little air sacs become compromised. Some of the alveoli, particularly the smaller or older ones, slowly but surely start to deflate, they collapse, and they stick together.
Why does that sticking happen? Is it just like air pressure escaping?
It's surface tension and a lack of pressure differential. Think of the alveoli like incredibly thin, tiny balloons. If you only inflate them partially and repetitively, the walls start to touch, and the surfaces, which are wet, begin to stick to each other. To use a good analogy, let's go with the instant noodle analogy.
Okay, I'm listening. I like instant noodles.
Imagine those dehydrated instant noodles in the cup, right? If you only put in tiny, shallow drops of water over and over again, that's your shallow breathing, some of those bits in the middle stay dry and they stick together and they shrink down and clump up. They're functionally useless. They are not absorbing the water. And in the case of your lung, they are not exchanging gas.
So the surface area for gas exchange just drastically decreases, which means you're getting less oxygen with every breath, even though you feel like you're breathing normally.
Exactly. The body has to solve this major efficiency problem constantly. If those delicate air sacs collapse, which is a condition called atelectasis, they just stop working. And that makes all the surrounding healthy areas have to work harder, which puts a ton of stress on the whole system. You need a massive systemic pressure flush to pop them all open again, to force those sticking surfaces apart.
And the body's mandatory built-in solution for this pressure flush.
That's the sigh. The sigh is essentially a pre-programmed mechanical reset. Doesn't look like a normal breath. It actually starts as a normal breath. But just before you exhale, your brain triggers you to take a second, much larger breath right on top of the first inhalation. It's the only way to generate that super high pressure needed to pop open and reinflate all those collapsed air sacs. It's an augmented breath designed for life maintenance.
The stakes here, then, are existential. I mean, if this involuntary reflex fails, lung function would rapidly degrade.
Lung failure is the consequence. If you don't execute a sigh every 5 minutes or so, the cumulative collapse of the alveoli is fatal. And we aren't just speculating here. We have historical proof of how vital this reflex is. Think about the era of the iron lung.
Oh, right. Those terrifying mechanical ventilators of the past, used for polio patients, which encased the entire body.
Right, and they provided continuous, constant volume ventilation, the same exact amount of air in and out, indefinitely. Patients in those early iron lungs suffered these terrible complications because they never spontaneously sighed. That continuous shallow volume meant their alveoli slowly but surely collapsed, leading directly to fatal lung failure. The doctors eventually realized that they had inadvertently suppressed a vital survival mechanism. It highlights how utterly non-negotiable this reflex is for life.
That historical context is sobering.
Oh, wow.
And it connects directly to modern critical care, right? Specifically mechanical ventilation, or MV. If you put a patient on a standard ventilator today, you're still suppressing that natural, varied breathing pattern.
Absolutely. When patients are on constant tidal volume or CVTV mechanical ventilators, receiving the same measured amount of air with every single breath, they can suffer from something called ventilator-induced lung injury, or VILI. And our sources detail 2 specific ways the lung gets damaged in this scenario, which is really crucial to understand.
Okay, so let's separate those 2 types of damage. What's the first one?
First, you have something called atelectrauma. This is the injury caused by the cyclical opening and closing of those collapsed or partially collapsed air spaces. Every single time the collapsed tissue is forced open and then allowed to collapse again, it causes shear stress and damage to that delicate tissue.
So that's literally the damage from the sticking and unsticking over and over.
Correct. But then you have the second problem, volley trauma. Because some alveoli are collapsed and not working, all the incoming air volume from the ventilator is forced into the few remaining patent, working alveoli. This causes overdistension, or basically overstretching, of those healthy regions. Both atelectrauma and volley trauma trigger a massive inflammatory response throughout the entire body.
It's a paradox, then. The constant volume is too much for the working parts and too little for the collapsed parts. So the body's natural sigh, that big reset, must be the therapeutic solution.
Precisely. So researchers have studied adding sigh breaths, which are known clinically as recruitment maneuvers, to the mechanical ventilation routine. These are basically artificially introduced, deep, augmented breaths designed to perfectly mimic the natural sigh.
Okay, did it work?
Oh, yeah. In animal models, adding sighs, even at low rates like 20 to 40 sighs per hour, minimized lung injury significantly. The studies showed the sigh maneuver reduced key inflammatory markers, specifically IL-1, IL-6, and TNF, and it lowered oxidative stress compared to the animals on constant volume ventilation alone. The sigh, even when delivered by a machine, acts as a profound protective strategy against both the mechanical damage and the resulting inflammation. It's a simple mechanical solution to a really complex systemic problem.
Okay, I want to zoom in on the biophysics here for a second. You mentioned the sigh works every 5 minutes, but the study suggests that one mechanical reset can actually sustain lung compliance for up to 45 minutes. What is happening at the surface level to make that one deep breath so protective for such a long period of time?
That takes us to the magic material inside your lungs, pulmonary surfactant. This is a complex mixture of lipids and proteins that lines all of the alveolar surfaces. Its primary job is to reduce surface tension and increase lung compliance, which is, simply the ease with which your lungs expand. Without it, your lungs would feel like concrete and immediately collapse.
So normal, shallow breathing gradually degrades this compliance. And the sigh is what restores it.
Exactly. The compliance gradually decreases over time with normal shallow breathing as that surfactant structure destabilizes. And studies confirm that a sigh is needed every 15 to 45 minutes to restore lung compliance to its optimal level. The mechanical function of the sigh is so critical because it forces a structural rearrangement of that surfactant film.
Okay, let's elaborate on this rearrangement. Let's use our analogy engine. If the surfactant film is supposed to keep the alveoli from collapsing, what exactly does the massive pressure of the sigh do to stabilize it?
We can use the sticky film analogy to visualize this process. Surfactant is composed of different kinds of lipids. Some are saturated and some are unsaturated. The saturated lipids are the good, sturdy ones that resist tension. The unsaturated lipids in the water are less effective and need to be kept out of that main working layer.
Got it. Good stuff and less good stuff.
Pretty much. So when you take that massive high-pressure sigh breath, that double inhale, it's like a high-pressure cycle that aggressively compresses the entire surfactant film. This compression forces the saturated, robust lipids to pack tightly onto the surface layer, and it squeezes out the unwanted water and weaker components. This process is called compressional hardening.
Compressional hardening, so it's literally hardening the defense.
Precisely. It creates this highly organized, mechanically robust protective film that resists tension and collapse much better than a randomly distributed film. The sigh is using massive pressure to create a strong barrier that balances out the tensile force that wants to stick the walls of the alveoli together. This is a really dynamic perspective. The sigh isn't just popping open collapsed sacs, it's re-engineering the actual surface coating, making all your subsequent breaths easier and preventing collapse for the next quarter or half hour. It's preventative maintenance.
That mechanical reset is pure evolutionary genius. It's a constant, automatic fix for what is basically a fatal flaw in our lung design. But now we have to move from the biomechanics to the software. How does your body, every 5 minutes, decide, okay, surface tension has reached a critical point, time to sigh? We're moving from the lungs to the brainstem.
And here's where it gets really interesting, because we're looking for the operating system that runs this involuntary reflex. The system is governed by the brainstem, the ancient automatic part of your brain that controls breathing, heart rate, and sleep.
For neuroscientists, pinpointing the source of a fundamental behavior like breathing to a small cluster of cells must be the ultimate hunt, the holy grail.
It absolutely is the holy grail. The basic rhythm of breathing is generated in the brainstem within a structure called the Pre-Bötzinger complex, or Pre-Bötzi. This is the core pacemaker for breathing. But the sigh is not a basic rhythm. It's an augmented, specialized breath. It requires a different, specific trigger.
So research is needed to find the specific on-off switch for the sigh within that whole complex breathing apparatus. Tell us about the quest to locate this mechanism.
This involved an incredible collaboration between labs at UCLA and Stanford, led by Jack Feldman and Mark Krasnow. They decided to hunt for this mechanism in mice, which are surprisingly prolific sighers. They do it about 40 times an hour, and the goal was revolutionary. Identify the absolute minimum number of neurons linked to this fundamental survival behavior.
That sounds like searching for a single grain of sand in a vast desert of neurons.
Yeah.
I mean, how on earth did they narrow it down?
They used a process of systematic screening. They screened this enormous library of nearly 19,000 different patterns of genetic activity in mouse brain cells. They were looking for cells that express specific receptors linked to peptides, those little chemical fragments that act as messengers. And this massive screening effort finally zeroed them in on 2 specific clusters of neurons, about 200 neurons in total located within or near the Pre-Bötzi that were directly controlling the sigh.
200 neurons out of billions in the brain. That is shockingly small for a mechanism that prevents immediate organ failure.
It speaks to the efficiency of evolution, right? They then identified the core discovery. The exact mechanism that transforms a regular breath into a sigh is driven by 2 specific protein fragments, or peptides, known as neuromidin B, NMB, and gastrin-releasing peptide, GRP.
So these are the chemical messengers. They're the keys that turn the sigh on. Let's build out the remote control analogy here, because this is where the specificity becomes crystal clear.
Perfect. Think of the brain's entire breathing center as a complex remote control for your respiratory system, located right there in the brainstem. You have the main power button for normal, rhythmic breathing. That's the core pacemaker of the Pre-Bötzi. But you also need specific keys for special non-rhythmic actions. A yawn, a sniff, a gasp, or a sigh.
And the sigh key is activated by these 2 specific peptides.
Exactly. NMB and GRP are like the two specific remote control keys released by one small set of neurons. When the lung needs a mechanical reset, maybe due to accumulating alveolar collapse that gets detected by sensors, those key-releasing neurons fire. The peptides flood the system, and they activate the second set of about 200 neurons in the Pre-Bötzinger. And those 200 neurons then instantly activate the breathing muscles to execute the big, augmented, double inhale sigh.
Wait, so if they could stop those keys from working, they could literally stop the sighing reflex altogether. No way.
That's precisely what the experiment demonstrated, yes. They used antagonists, basically blockers, to interfere with the receptors for these peptides. They found that blocking just one of the peptides cut the animal's spontaneous sigh rate in half. But when they silenced both peptides, blocking both remote control keys, the animals stopped sighing completely. They could still breathe normally, but they lost the critical ability to reset their lung mechanics.
That is genuinely profound. The fact that just manipulating two tiny protein fragments can halt a fundamental, life-sustaining action. It just underscores how beautifully simple and orchestrated this automatic system is.
It also has profound implications. I mean, given the critical nature of this mechanism, the identification of the NMB-GRP Sigh control circuit raises a really important question. What happens if the switchboard becomes hyperactive?
You mean, what if the body starts sighing too much? That sounds like the opposite of survival mechanism.
It can be debilitating. This is where the neurological and the psychological begin to intersect. This tiny circuit suggests that physicians could eventually target these pathways with drugs. This could certainly help patients who physically can't breathe deeply on their own, providing that mechanical reset. But conversely, it offers a path to limit debilitating excessive sighing, pathological sighing that we see in certain anxiety disorders, or the rare Sigh syndrome.
So they might be able to just dial down the remote control if the person is constantly hitting the sigh button because of anxiety or something.
Precisely. If the neurons that release these peptides become overly sensitive or are being overactivated by other stress hormones, which we know happens, it leads to chronic hyperventilation and excessive uncontrolled sighing, which, ironically, increases anxiety. Targeting those NMB-GRP receptors could be the specific intervention needed to restore balance without interfering with regular breathing.
Okay, so we've established the sigh is a mechanical necessity, and it's orchestrated by a highly efficient, ancient brain circuit. But that still leaves the emotional sigh, the one we do when we're genuinely frustrated or finally relieved or when we are experiencing panic. We've now shifted from the brainstem survival mechanism to the conscious or psychophysiological act.
That's the next layer up, where the automatic and the feeling states merge. And our sources show a very clear link. Negative, high arousal emotions, such as panic, severe sadness, or high stress, all tend to significantly increase our spontaneous sigh rate, sometimes doubling or tripling it.
Why do our bodies naturally use that mechanism when we're stressed? Is the stress actually causing the alveoli to collapse faster?
Not necessarily faster collapse, but stress profoundly disrupts the rhythm of breathing. When you are anxious, your breathing pattern becomes less variable, more restricted, and often shallower, a condition called respiratory monotony. The sigh acts as a psychophysiological reset mechanism for that disrupted breathing variability. It forces the breath to return to a smoother, more flexible, regulated rhythm, which subsequently helps the brain and body calm down.
That's fascinating. So the emotional sigh is the higher brain system borrowing the brainstem's reset button to fix a different problem, a problem of chaotic or monotonous rhythm.
You nailed it. And this connection between physical breathing and psychological state isn't just intuitive anymore. It's actually measurable in the brain. This takes us to the concept of neuronal coherence.
What exactly is that?
Well, we traditionally think of breathing as just, moving the diaphragm and ribs. But research using EEG and even implanted electrodes has shown that the breathing cycle directly tracks and organizes neuronal activity across wide regions of the brain, particularly in the cortical and limbic structures, your emotional centers.
So the physical act of breathing is literally organizing brain activity, like keeping time.
Think of it with the orchestra conductor analogy. Your brain is a vast orchestra with all these different sections, including the amygdala and hippocampus, which are critical for emotion and memory formation. The conductor, the breathing cycle, ensures all these sections are playing together or tracking the same rhythm. This coordination is visible in the brain's electrical signals, specifically in the high-frequency gamma band oscillations.
Why the gamma band specifically?
Gamma oscillations, which are around 40 to 150 hertz, are crucial because they're linked to higher cognitive processing and linking distant brain regions together. When breathing becomes irregular or monotonous because of stress, this coordination or phase locking breaks down. The orchestra just gets chaotic. The sigh, by forcing a massive deep breath and reset, immediately restores this phase locking. It forces temporary neuronal coherence and restores a sense of internal rhythm and organization, which translates into a rapid reduction in panic or anxiety.
That is the perfect bridge. Because if the sigh is such a powerful fundamental reset for both the lungs and the brain's rhythm, can we intentionally use it? Can we consciously hijack that brainstem tool for a massive psychological benefit rather than just waiting for our body to hit the automatic button every 5 minutes?
And this is exactly what the modern quest for breathwork sought to answer. They wanted to know if we could actively leverage the sigh for well-being.
Tell us about that study. It was a randomized trial comparing different types of breathing against traditional meditation, right?
Yes, it was a fascinating randomized control trial. Participants were asked to dedicate just 5 minutes daily for 1 month to one of 4 practices. There was a cyclic sighing, box breathing, which is, equal inhale, hold, exhale, hold, cyclic hyperventilation, rapid breaths followed by a long exhale, or a control group practicing mindfulness meditation, which is the passive awareness of the breath.
The methodology is really important here. They weren't just testing relaxation, they were testing active volitional control against passive awareness.
Absolutely. The goal was rigorous. See if actively imposing a specific respiratory rhythm could provide superior benefits to mood and anxiety compared to the passive observation that's central to mindfulness.
And the dramatic reveal. What do they find?
Well, while all 4 groups, including the meditation group, reported some reductions in state anxiety and negative affect, the clear and significant winner for improving mood and reducing physiological arousal was cyclic sighing.
So cyclic sighing outperformed traditional mindfulness meditation in increasing positive affect. That's huge, given how popular mindfulness is.
It was a very strong effect, specifically in increasing positive affect, meaning subjects reported feeling better, happier, and less stressed, not just less anxious. And importantly, the benefits grew larger the more days subjects adhered to the cyclic sighing protocol. It seems intentional control with this specific pattern is more effective and provides a faster, clearer emotional payoff than just passively observing the breath.
Let's break down the mechanics of cyclic sighing again, because it really sounds like we are literally just copying the physiological survival reflex.
We are. That's exactly it. Cyclic sighing emphasizes a prolonged exhalation, which is the calming phase of the breath. But critically, it incorporates that core physiological element of the natural sigh, a double inhale to increase the depth of inhalation. You take one inhale through the nose, then you quickly top it off with a second smaller inhale to maximize lung volume, and then you follow that with the longest, slowest exhale possible through the mouth. You are consciously mimicking the Brainstem survival tool, turning it into a repeatable therapeutic practice.
So we found the conscious hack for the involuntary system.
We have the blueprint. And the data shows it works not just during the 5-minute session, but causes lasting physiological changes beyond that practice period. If we connect this knowledge to the underlying physiology, we can really talk about why cyclic sighing proves so effective compared to the other breathing methods. It directly leverages the body's established calming systems.
You emphasize that the prolonged exhale is the key component. Why does extending the exhale provide such a powerful, immediate calming effect?
The prolonged exhale directly engages the vagal nerve, which is the main highway for the parasympathetic nervous system, our rest and digest mode. When you exhale slowly, you activate this system. This increases what we call vagal tone, which is essentially the strength of your vagus nerve activity. And when vagal tone is higher, it tells your body to relax.
So if the inhale is activating, the exhale is the brake on the system.
Exactly. When the vagus nerve is engaged, it slows down the heart rate. It's a phenomenon scientists call respiratory sinus arrhythmia. And this mechanism, the direct link between a slow exhale and a lowered heart rate, is the fundamental physical link connecting your breath to physical calming.
But the most stunning takeaway about cyclic sighing wasn't just the acute calming effect during those 5 minutes, it was the long-term impact on baseline functioning.
That was the mic drop finding. Participants who consistently did cyclic sighing for 5 minutes a day ended up with a significantly lower resting breathing rate throughout the entire day. And that's compared to the box breathing, hyperventilation, or even the mindfulness meditation groups.
Meaning, they weren't just calm for those 5 minutes. Their baseline physiological state actually shifted toward calm over the entire month. Their respiratory rhythm set point fundamentally changed.
That's the interpretation. It suggests the practice literally resets the respiratory network's default mode of operation. You are, in essence, teaching your brainstem, which is always monitoring, that a slower, more deliberate breath is the new normal.
I want to circle back to the psychological benefit of this being an active tool, not a passive one like meditation. Studies show that when we intentionally control our breathing, we engage specific higher brain circuits that directly address anxiety's core complaint, loss of control.
That's a crucial distinction. We've seen that the intentional volitional control, like actively manipulating the breath to go faster or slower, engages the frontal, insular, and temporal cortices. These are the areas involved in motor functions, planning, and executing an action. It is the feeling of doing something.
And if you're anxious, having a tool that you can actively do to immediately shift your physiology has to be incredibly potent.
It is. Perceived loss of control is the major hallmark of anxiety and panic disorders. So having a tool, the Cyclic Sigh, that directly modulates your respiratory rate, engages the vagus nerve, and immediately lowers your heart rate. It offers a concrete psychological relief that simply passively attending to the breath during meditation might not provide as acutely. It's an immediate, verifiable feeling of having control over the life force itself.
So we have the complete picture now. The involuntary sigh is a mechanical necessity for lung survival, and the voluntary sigh is a neurological necessity for psychological regulation. And these two functions are tied together by that tiny, elegant cluster of 200 neurons in the Pre-Bötzinger.
And this convergence is now the focus of serious clinical research, which really highlights the clinical potential. Knowing the mechanism means we can develop hyper-targeted therapies.
Let's look at the mechanical application first. How is the sigh being used in trauma settings?
Well, the ability to mechanically reset lung function every 15 to 45 minutes via the Sigh is being tested in modern intensive care. We can look at studies like this event trial for trauma and acute lung injury patients. The concept is that instead of the rigid, constant volume ventilation that causes villi, the injury we discussed, they implement a strategy called spontaneous sighing ventilation, where the machine is programmed to periodically deliver those augmented sighs.
So we're automating the body's own protective strategy to mitigate inflammation and damage.
Exactly. It uses a physiological mechanism, not just a mathematical formula, to protect the lung tissue. And second, the neurological application for disorders of excessive sighing is equally compelling.
Tell us more about using this knowledge to manage conditions like the Sigh syndrome.
The precise mapping of that NMB GRP peptidergic Sigh circuit opens a huge door for drug development. We know that conditions involving excessive, irrepressible, persistent sighing, which can often precede or accompany panic attacks, are typically preceded by trauma or severe chronic anxiety. This suggests an overly sensitized respiratory network.
And what's driving that hypersensitivity?
Research has strongly implicated the hypothalamic neuropeptide orexin. Orexin is the key system that drives wakefulness and acute arousal, and it's intrinsically linked to panic states. And it turns out orexin strongly modulates and activates the Sigh circuit. If that system becomes hyperactive due to chronic stress or trauma, it just cranks up the NMB-GRP signaling, leading to chronic anxiety and debilitating hyperventilation.
So the goal would be to target the NMB-GRP receptors in the brainstem to turn down the volume on that signal.
Yes. And the advantage of targeting those specific receptors is that it dampens the excess signaling that leads to that pathological frequent sighing without necessarily interfering with the core rhythm of normal breathing. It offers a surgical approach to managing panic-related respiratory dysfunction.
The Sigh truly is the body's most effective, elegantly simple, self-regulating tool. It is constantly fighting mechanical failure in the lungs, preventing organ collapse, and simultaneously offering an immediate reset switch for cognitive and emotional stress in the brain.
The knowledge that two tiny clusters of neurons, communicating via two protein fragments, orchestrate a behavior that prevents organ failure and regulates our deepest emotions. That convergence of necessity and therapy changes how you interpret every single deep breath you take.
What does it mean that your most powerful, scientifically validated tool for calming your brain and improving your mood, cyclic sighing, is simply turning the body's involuntary life-sustaining reflex into a deliberate, conscious practice? You don't have to wait for the stress to peak. You can listen to the whisper of the sigh and deliberately turn that reflex into your immediate control.